At the Auto Innovation Centre, one of the things we're best known for is our very high quality 3D scan data. We have a fleet of vehicles and we bring them through and we scan them as much as possible to sell into data packs for you so you can develop your accessories. From time to time, we do get asked questions about what's included, the file type, and how it should be used in your CAD program. So today we're going to jump on the computer and have a quick look and see if we can answer some of those common questions and provide a couple of solutions of how to use that data. Of course, there are plenty of different ways to do it, but come along with us and hopefully this will take care of some of those questions for you now.
So how are our data packs sold? Well, they're sold to suit the development of the product at hand. So typically, you can see here there is an alternator, battery, frontal protection system is very popular, GVM upgrade, interior, and so on and so forth. So it's broken down into manageable pieces because there's a lot of data that's not really feasible to sort of buy as one big chunk. And typically people will be looking to develop a particular product or a set of products from that. This is our upcoming subscriber portal. And if you go in here and let's say we pick, say, underbody protection, you'll get a screenshot of what's included and it gives you a bit of an idea of the areas that you'll get data for. It has a price, you can add to your cart and you can buy it. It does tell you that there is 46 STL files in here and 72 photos and a couple of IGES files. So what's actually in the data pack? Well, when you download the data pack, you'll get a link to it. You'll get access to this to a drive that looks like this. This is a GR Yaris brakes, and there is a series of STL files and IGES files. Everything that's part of the data pack, which you know, that are all your CAD files, and then there's a series of images. And we do provide images because sometimes it makes it a lot easier to see actual photos of the parts to help you decipher other part numbers, things that you can't see in the scan data, or sometimes you just need a little bit of help to see what you're actually looking at, and a photo can help. Where possible, we scan parts individually, so you can see there's a brake caliper individual to brake pads, the rotor, the hub, and things like that. We do that so you can get the best possible resolution for a scanned system. And you can see the backside of the components, you can see the interface, and it makes it massively better than just scanning what's sitting there as it sits there. And anyone who's used our data packs can attest to that. There's another very important reason, and it gives you the ability to toggle off each item when not in use. So that'll take a fair bit of load off your computer's GPU. And this is really important, and it's one of the key reasons why our data packs are the best, because your computer's not chugging constantly and crashing every 15 minutes, which inevitably slows your product development. We do include pretty standard stuff in there in a lot of data packs, like a ground plane, because our data isn't typically aligned to the ground, it's aligned to the chassis, or you know, if it's a data pack that's predominantly a body like a roof rack data pack, we'll just make it symmetrical around the body. And we also include additional things. So you can see that with a frontal protection system, you get a very big chunk of the car's bodywork, as well as the bonnet, which gives you the ability to conduct the appropriate amount of styling on the data pack, because it's a bit hard to do if it's just the front end. So the next step would be to download all the data that's in this pack here. Get it onto your PC. Now you have purchased the right to use this data. It is very important that, you know, we're not selling the actual ownership of the data, because it's not to be on-sold. It's not for resale. It's for you to do whatever you want to do with it within your business. But, you know, it is priced accordingly. So hopefully, you know, people realize that it's just to be used for your product development. And then if other people need it, they can buy it, because it does cost a lot of money to make, and we hope everyone likes it, and it is pretty good value for money. Once you've got the data downloaded onto your computer, so the next question we get is typically, what is an STL and how do I use it? Well, when a laser scanner like the one that we have, scans a part, it throws down points all the way across the part, separated by somewhere between 0.4 and 1 millimeter. That's the distance between them. And this is kind of what it looks like. So every single, you see it's like a little net here. Now, each of the actual points, so the bit where the lines intersect is the point. And these points effectively form the surface, realistically, of the part that's been scanned. It's kind of hard to see with the resolution, but you get the idea. And this is known as a point cloud. Now, you don't get a point cloud, but you get, but that's the important part. That's the most accurate part, because each of these dots has an accuracy in the virtual space of about 0.04 millimeters or under. Now, the next step is that this point cloud is turned into an STL, which is what you're looking at here. This is an STL. And what happens is that each of the points is connected with a series of vertices. So say, that each of these straight lines is a vertice, and every single one makes a triangle. So what you're left with from an STL point of view is every single one of those is joined up to make a triangle, and you get something that looks like this. So it's just a big series of triangles. If you zoom in enough, you can see them. So, and then finally, if you, the display here is going to be pretty important, what you select there. But you can see here that this is what the series of triangles looks like, with a little bit of like CAD smoothing in there as well. Now, what's wrong with STLs? Well, some CAD programs are fantastic with working with STLs. But the majority of our customers use SolidWorks or something of a similar level, and they have less functionality with these STLs, and historically they've had a bad reputation for how they handle those STLs. The issue is always that you can't click on it, you can't do anything with it, it's just a big graphic, and that is kind of true to a degree, but there is certainly some interaction you can do with the STLs, and I'll show you how. So we'll get to processing in a minute, but one of the first things to consider is when you're importing an STL is you've downloaded them from our server, and you have a series of STLs in a folder. The next thing I do, and all of this advice is there's plenty of other ways to do it. This is just a way that you can use to get started if you like to, and I'm sure you'll find a better way eventually that suits your processes better. But I just drag and drop it straight in. So if you go into Tools and Options, you go to System Options Import. If you choose the format, so basically this is how you choose how you want to import the parts, import the files, sorry. And STL, so STL OBJs off apply to, you're going to say whether you want to import as a solid body or surface body. Import it as a surface. It usually doesn't like constructing a solid out of some scan data. And units is millimeters. Now, a common problem we've come across is units might be set to centimeters or even inches or something like that. And people will call up and they'll say, hey, my car is, 25 times bigger than it should be, or 10 times bigger. And that's just a unit issue. So basically what that's saying is when it gets the file format and a unit of 1, what is that unit? It's millimeters. So that's the first thing, is to make sure that your units are correct. And the other thing is you want to make sure that you bring them in on the right coordinate system. Now, I've just dragged and dropped this, and what it does is if I click on origin, you'll see the origin is over here somewhere, which seems like a long way away, but it will all make sense. Now, this is a rear pad. Which means that probably makes sense because that will be the center of the car, probably the front of the bumper, and this is where the back looks like right rear pad lives. Oh no, could be left. There you go. So make sure you keep the coordinate system correct. Now, the next thing that I choose to do, which is not necessarily essential, is I just save this out. Click save it as a part. Do nothing else, and it'll still save it as a graphics body, but it'll be in a part format. And that's important because the next step that I choose is to import that into an assembly, which I find a bit easier when they're a part. From now on, we're not going to save that. What we want to do is we want to create a new assembly. and we're going to start bringing parts in. I'll start with the brake rotor. Now, this again, this is very, very important. If I click and place this in the window, it will put it wherever I've clicked. However, if I just tick, it will actually put it with the coordinate systems aligned between the part and the master assembly. Now you can see here again, we've got all the vertices and all of the point cloud in there in the STL. I'm just going to go to shaded because shaded does give you a bit less load on the system. And then from here, all I do is continue to go through and just select parts, which I've just gone insert and I've ticked a new part. I'm going to tick yes. And it's as simple as that. And you just bring in every single bit you need. Bring in the upright. Again, it waves around. And you see they're all dropping into place, just like a wonderful jigsaw puzzle. And then once you've finished with it, you can actually pop this out and set colors. So you can get the appearance and you can change the colors. And I find that also helps to distinguish where the parts start and stop. But I've got one that I did earlier, which you can see here. So this is each of the parts brought in, and I have given them a bit of a different color. So they've all got a separate color. And this is basically the front end. Now, don't be alarmed that the brake line goes to the wheel. That's obviously as a byproduct of scanning the caliper separately. But the beauty of this is now you can just come in and you can see what each of your parts are and just turn it off. So when you're working on this and you want to see how it all fits, all the pads line up. The wheel's been turned off so we can see what we're dealing with here. You can turn the rotor off and you can have a look at you can see the offset of the rotor. You can see the knuckle and everything else you need to do. This is really important because when you're doing product development, you want to have some stuff on and then you want to turn it off when you're not using it because it does put a lot of pressure on the computer and the GPU, and you do need a very powerful computer to run scan data and CAD systems. Now, we spend a lot of time aligning all of our data to planes. So if I click on the right plane, you'll see that it runs, that would pretty much be the center of the car. In the case of the brake data pack, it looks as though that'll be the front of the vehicle or front of the bumper, being a GR Yaris, and it's been placed symmetrically. Now, you can choose to use this plane as your centroid of the vehicle, but depending on what you're developing, you might want to pick something more localized. So what we have now is what you would call a nice reference data pack for you to start working with and designing products with. Say you want to develop a product to go into this. The most important thing to take into account is the fact that these are scans of manufactured items. So these items are not perfect because nothing is made exactly to CAD. So you have to work with a datum and you have to stick to that datum because there is nothing on here that is parallel or perpendicular or concentric with one another to CAD levels. So to 0, 0, 0, there's always going to be a tolerance there. So let's just start with how we would work with an STL. So I'm going to open this part up and you can see that I always seem to need to turn that off. Now, how do you work with an STL? Right, so say you want to redevelop the hat of this rotor. The point cloud is the accurate stuff that you really want to work with. That's the raw data that's absolutely most accurate. I mean, the STL vertices are going to be quite accurate as well, but if you don't need to, then just use the points that have come straight off the laser scanner. So I can make a plane here as my datum. So if I wanted to make something that remake, say the hat of this rotor, I can pick this front face here because it is the it's a CNC machine part and it should be fairly accurate. So I can just go pick plane, and I'm going to make a plane. Now you notice that I still can't click on it, but if I go down here to the filter and I pick mesh vertices, it will allow me to come in and just pick them. And I can pick 3, just like that. I can say yes, and I've made a plane that is the front face of that rotor. And if I wanted to check that, there's probably better ways to do it, but I can just chuck a quick sketch on there, and I'll extrude it to the tune of, say, 0.02 millimeters, and see. And again, this is where giving stuff an appearance can really help. So my go-to is always bright pink, and it gives you a bit of vision there. Now you can see, depending on how accurate you want to be, like that's going to be within a very small number of decimal places of angle, but you can edit the feature and say, well, okay, well, I'm just going to change one of these and see if that would change what the fit's like. You can see that's a bit better. You can see that it's a little bit low over here, but so tiny. And if you spend a couple of minutes, you could probably get it even better than that. Now, then, say we're pretty confident with that, we can just get rid of this little sketch that I did. And we know we've got a plane that's on the front face, which is fantastic. And, big fan of naming the planes too. So you could call it datum, make sure you're aware of, what it is, and you don't lose track of it. I'll make it a bit bigger if I can grab a hold of it here. And you're good to go. Now, the thing is, there's a couple of things to know here. You've obviously got to know the part you're working with. So in the case of this is called a floating rotor. And this ring kind of wobbles around and isn't really located to this one. I mean, it is located, but it has some degrees of freedom to allow it to perform as a high-performance brake rotor. So you cannot rely on it being concentric or parallel to this hat. So you've got to make sure you're working with the right thing there. Maybe treat them separately for the purpose of what you're doing. And you could even, probably could even turn it off, let's be honest. So they're separate parts there and you can chop and change. But there's a number of different ways you can do it. It's entirely up to you. But say from here, I mean, you can do plenty of things. We've made a plane, so we've worked with an STL, which is great. There's other things that you could do. You could do an axis. Now, say you want to do an axis about the center because you want to design the part and make sure that you know where its center is. You can actually go to make an axis based off of a cylindrical face and paint selected facets. And then it allows you to come in and paint a few of these faces. So this is a CNC machine edge that will be done in the same operation as that front face. So they should be as perpendicular gets. But what I'm doing here is just painting a few spots. Obviously, if I really want us to be super accurate, I might go a bit more than that, but that's probably going to do the job. And you can see that it's plonked an axis down, and it looks pretty much in the center, which is good. So we made an axis. Now, that's a great tool as well. However, there is one problem with that, and that's if we look perpendicular or normal to this plane, so completely normal to our datum, and I zoom in on this axis, where is it? You can see that I'm not looking perpendicular to this axis because it's done a best fit of the facets that I painted. So that would be a problem. If you try to design something, you wouldn't be able to select the axis because it's not perpendicular. So what you're better off doing is creating a point, and the inputs I'm using is the datum plane and the axis, and it's going to say, I'll give you an intersection. So what it's done there is it's given me an intersection point on this plane, but where the axis crosses it. Now, that's going to be very, very close to the center of this hat, and I'll take that, and I'll say thank you very much. And then now I don't really need the axis, but I could remake the axis through that point. But effectively, I know now that if I was to do a sketch and we'll just hide that axis. I know that this is going to be very close to the center of this hat. So if I round it out to here somewhere, you can see that it's a pretty good fit as it runs around. And that is super important to make sure that your datums all work with each other, because if you go and make another datum somewhere else and they'll be out by 0.002 of a degree, it's just not going to work in CAD. So start with your datum, pick the correct datum and work from that. And you can pick a plane that is perpendicular to the first plane at a point. So say you've got a front chassis rail, you might want to make the datum plane off the front end. And then you know that the chassis rail is meant to be perpendicular to that, but they obviously have a level of manufacturing tolerance in them. So you'll say, well, I want to make a plane that's perpendicular to the front one, and then pick the side of the chassis. So there are plenty of ways to do it. Just make sure you're always referencing off of that datum plane. So from there, you can see how that this assembly can be your reference that you can put into your product development. It can be just a part, but you can take it from here. You can work through it. You can create plain sketches. I find the little trick that I did where we extruded a surface really helps in terms of seeing how they fit. So if I probably didn't make that one big enough, but you can, and then changing appearance makes a massive difference as well. But you can see how if I made it a bit bigger, you could check the fit around the side. But that concept works really well. And you know, when you get scan data like this that's half patchy, that's very, very close to a fit. So I hope that's been insightful. You can use STLs in SolidWorks. There's plenty of other things that you can do. There's all sorts of science, but in reality, you know, their functionality is most useful in a graphical representation, and the fact that they are accurate. So you can hang your hat on the accuracy being 0.04 of a millimeter effectively for each point cloud. But do always check it. Make sure everything looks like it fits okay. So, you know, you're gonna want to come in here and you know, make sure the pads are fitting up and, you know, they're in the right spot. You can see there's chamfers on them there, but you can see that they're fitted right up against the rotor. We do our best to make sure they are always perfect. They're as perfect as they can be. That's how we get the car, and we scan the data as the car is made effectively. So I hope that's been insightful. It really is great to use. You do need a powerful PC, but give us a call if you've got any questions. But hopefully this has answered a lot of them, and it makes it a bit easier for you to do some product development.